Welcome back to A.R.T's Real Repairs for Real Customers, the smallest active channel on YouTube. But we serve the interest of mobile repair techs everywhere. I have finally got around to covering a PowerPoint presentation from many years ago on the subject of paint blushing. Now, some paint companies offer some information about this and offer some products to deal with it. But I find that they often don't spend enough time discussing the science and the details behind it. But I've always felt that understanding the details would make for a better craftsman. Now, it may be a while since you've reviewed the science, but at any rate, we need to include this chapter on our channel, and we may as well have some fun doing it together. So let's go. First of all, what is paint blushing? Paint blushing occurs when moisture affects the surface of wet paint, especially paints containing organic solvents. Now, when we hear the term organic solvents, we are thinking about solvents that have carbon as a component, particularly those that are petroleum derived. These evaporate as the paint dries. Therefore, they are called VOCs, or volatile organic compounds. Volatile meaning that they evaporate, the solvents escape into the atmosphere. So paints emit these VOCs as they dry. You can smell it, can't you? Proof of those VOCs off-gassing, as they say. In fact, many air fresheners or perfumes cover other odors by releasing their own VOCs. But the question is, how can the evaporation of these VOCs result in moisture affecting our newly painted surface? There are two basic principles that are involved here. The first one is evaporation is a cooling process. How is this true? Well, we all have experience with this. When getting sweaty doing yard work, we're thankful that the evaporation of our perspiration cools us down. Without that, work could be life-threatening. Hey, that sounds like an excuse I could use. So for any liquid, including our paint, molecules that leave the liquid have the most energy. So they're taking energy with them. And because of the law of the conservation of mass and energy, the net energy of the remaining liquid decreases, meaning the temperature of that liquid goes down. Faster drying solvents cool the surface quickly and to a lower temperature. So the faster the evaporation, the lower the temperature. So as you might imagine, for the duration of our discussion, energy is our key focus. You may have had a doctor spray ethyl chloride on your skin to temporarily freeze the skin to eliminate the pain of an injection. That's got to be a super fast evaporating liquid right there. Let's see the theory in action here on this old salvage seat. The current temperature of the vinyl is 73 degrees Fahrenheit. Now I'm wiping with acetone, the fastest drying solvent that I carry on the van. So now the temperature of the vinyl has dropped about 15 degrees due to evaporation. More important, though, is that the cool vinyl will cool the surrounding air. What effect will that have? Well, that brings us to our second principle, that cool air cannot hold as much moisture as warm air. Yes, warm air can hold more moisture. You might say that it gets weaker as it cools down and has to let some moisture go. In warm air, water molecules have more energy and therefore move about as a vapor, which by definition is invisible. In cold, dense air, water molecules have less energy and therefore attach to each other due to surface tension. This produces liquid water that we can see. And we've all experienced this with a glass of ice water on a humid day. The air surrounding the glass is cooled. Water falls out and condenses onto the surface of the glass. So the same thing happens with our paint. As evaporation is causing cooling, water condenses into our paint, and we see a hazy whitish effect which distorts our target color. Now, here on a rainy day, we are spraying our salvage seat with an aerosol solvent paint. The temperature drops from 75 degrees Fahrenheit to 63 degrees, a 12-degree difference. And that makes sense because we would expect a slower drying solvent than the acetone we used previously, so that the paint would flow out a bit before drying. After a few minutes, we see some blushing in spots. By the way, this happens also with water-based paints when it's extremely humid. You will see blushing in spots depending on the makeup of the seat and the temperature in the various areas of the seat. Another factor is that when you overlap the spray pattern, you may have some areas that have heavier paint than others. After some more time, we see the whole panel has blushed and is now starting to warm back up, indicating that evaporation is finishing up. And the same principle holds true with our air dry fillers. If they're cool, they're not dried yet. Once they're warm to ambient temperature, the evaporation is stopped. Now we've seen these two principles demonstrated, that evaporation is a cooling process, and that cool air cannot hold as much moisture as warm air. How can the technician put this knowledge to work? One of the best tools a technician has is knowledge of the dew point. And for the mobile tech, a definition of dew point would be the air temperature at which moisture will blush your paint. So it's the air temperature at which the air has 100% relative humidity. When the temperature drops to the dew point overnight, you will expect to see water droplets on the surface of objects. While we discuss the dew point, we have to remind ourselves that all three states of water exist in the atmosphere. Water as a solid in the form of ice crystals or snow, water in the form of liquid such as clouds and fog, and water in the form of water vapor, which is a gas, which is invisible. The point is, our atmosphere can hold a tremendous amount of water. So a weather app on your phone can be really helpful to see what the dew point is before painting. In this scenario, the temperature is 83 degrees. The humidity, relative humidity, is only 14%. So not much chance of blushing. We'd have to get all the way down to 30 degrees temperature before we would see 100% relative humidity, because the dew point is 30 degrees. Now, even in the desert, it can get pretty cold at night. So if there's any humidity at all, you might get some condensation if the temperature drops that low, and you can collect the condensation and survive. One thing you know for sure, you will have no paint blushing at all. Let's take a look at another scenario. Here the temperature is 55 degrees. Looking down, we see the dew point is 55 degrees, the same as the current temperature. And the humidity, therefore, is 100%. That's what we would expect. And we would also expect to see some precipitation at this point, some condensation, and indeed we have fog. That's exactly what we would expect. Here's another scenario, and I feel like I'm on a field trip with Science Club. It's 6:20 a.m. I have a 2-hour drive to another major market because no techs there can do the repair or make the color. But that's for another story. Notice the temperature is 68. The dew point is 65, only 3 degrees difference. And the humidity is at 90%. But look at the tree line. There's fog. meaning the relative humidity over there is 100%. So one of two things are likely true. Either there's higher moisture content over there, meaning the humidity is 100% at 68 degrees, or the temperature in the shade of these trees is 3 degrees lower than the 68 degrees at the weather station. And 3 degrees lower over there is all we need to reach the dew point. However, just knowing our scientific principles, we're able to read our surroundings and wouldn't even need the app. Now, if we happen to be doing boat repairs today, which we're not, we will be using solvent paints. And we can see the dew point is only 3 degrees removed from the temperature. So this would not be a good morning to be spraying solvent paints, would it? But what could we do? We could match the color in advance. We could do all of our repairs, and if it took us an hour to do all the repairs, then by then, maybe the humidity situation would be different. We've heard that the fog lifts or the fog burns off. In fact, if we look at our picture, we can see that the fog exists here where it's shaded from the sun. Where the sun is shining, there is no fog. Let's use the steam from this pot to represent our fog. Is steam a vapor or a liquid? Remember, water vapor is invisible. True steam is actually invisible water vapor. Steam that you can see is usually given the term wet steam, but it's actually water droplets suspended in the air, just like the fog. If we add energy to this steam, would it burn off like the fog into invisible water vapor? We can use the kitchen torch to give a bit of energy like the sun when it shines on the fog. Now, our energy source has not changed the actual humidity. We've lowered the relative humidity by adding energy. We've lowered the relative humidity by raising the temperature. So the expression, the fog burns off, holds water after all. Let's briefly look at a couple more examples. Here, the temperature is 64 degrees. The humidity is 94%. The dew point is 62. It's only 2 degrees away from the current temperature. But it's raining. Why? Well, it's raining up there. It's only falling down here. The temperature drops about 5 degrees for every 1,000 feet we go up. So the clouds at the dew point could be at 1,000 feet. In this example, the temperature is 58 degrees, which is 8 degrees higher than the dew point, yet we have a light rain. Could it be that the clouds are at 2,000 feet and it is there that we've reached the dew point? Well, we can't say for sure. There are lots of other factors that we have not considered, but we're not meteorologists. There's the wind, and there's also the barometric pressure. But all we want to do is just get this correlation between the dew point and the current temperature in order to determine if it's safe for us to paint or not. So we are well on our way to answering the question, what can we do to prevent blushing? What can we do to correct blushing? And if energy is involved in the problem, isn't it reasonable to conclude that energy is also involved in the solution? With paints using an organic solvent, a slower drying solvent or even a retarder can be added to retard or slow the rate of evaporation, thus reducing the cooling effect. Reducers are often labeled as slow, medium, or fast. So when there is a risk of blushing, pick a slower reducer. Be careful when using a retarder because it dries so slow that it will make a glassy, too shiny finish. I did that on a rainy day on a dash about 40 years ago. We won't do that again. Of course, this first option on our list is not applicable to aerosols since we can't adjust the content. Here's a little trick. Warm up the part to be painted ahead of time. Get a head start on the energy. Dry heat could be added as in a paint booth or directly with a dry heat source such as a heat lamp, a heat gun, hair dryer, or maybe the vehicle's heat turned on. Ideally, a paint booth would have the means to keep the humidity and the temperature constant, meaning your paint mix could be exactly the same every time. Remember when using the hair dryer that our main focus is not the paint per se, but the air surrounding the paint. And turning the vehicle's heat on does not exhaust any humidity when it's already humid outside. So you have limited help there. On our same salvage seat on the same rainy day, we have sprayed some more paint from the same aerosol can, but we're using a hair dryer to warm up the paint surface, and therefore the air immediately surrounding the paint. And even after some time has elapsed, we still have our target color. So we can use our mobile app to check the relative humidity and the dew point. If the relative humidity is 85% or more, consider not painting. It's often best to wait and do it right. So as we're thinking about correcting a paint blush situation, we have to mention that adding another layer of paint is not going to help. That will only result in more evaporation and more cooling. Of course, we know that. So instead, it's necessary to fully dry our paint application. You will know that the evaporation of the solvents is complete when the temperature of the painted surface returns to the ambient temperature. Once the paint is dry or cured, as needed, you can lightly sand or buff the affected surface. It could be that the moisture didn't penetrate too far into the paint film. As we mentioned, it's still possible to have some blushing in a water-based paint. However, sometimes you find you can wipe the surface with alcohol, and that will reconstitute the surface, melting it, if you will. So after all that is done, then we can recoat following the suggestions under the list prevention, which might even involve waiting for some better weather. And if you've stayed with us up till now, congratulations! We do have some supplementary information for those of you that are interested, where we're going to compare a dry heat versus a wet heat. We've already mentioned some dry heat sources, but now let's take a look at wet heat sources. And for our industry, let's define this as combustion that puts water vapor directly into our work area. Those sources could include hydrocarbons, such as those derived from petroleum. It could be alcohol as a fuel source, such as ethanol, or it could be wood. This graphic is oversimplified just to follow the logic. We know combustion of a hydrocarbon would mean combining it with oxygen. So we have the hydrogen and the carbon each combining with oxygen. Logically, if hydrogen combines with oxygen, we could expect H2O or water. Similarly, the carbon part mixing with oxygen, we could see how that logically could bring us carbon dioxide. We see here that the combustion or the combining of ethanol with oxygen yields carbon dioxide gas and water vapor plus heat. Similarly with the propane, we combine that with oxygen and we get the same yield, carbon dioxide and water vapor plus heat. So we get heat that we can feel and some light that we can see, but we can't see the carbon dioxide or the water vapor. But when a jet goes overhead, you may see a vapor trail from the combustion of the jet fuel. It's actually not a vapor trail, it is a contrail. You have water vapor coming out of the engine, and being that high up, it's so cold that it instantly turns into ice crystals. You may have thrown hot water into the air in the middle of the winter and seen it change to ice crystals immediately. Same thing. Much like an algebraic equation, the parts have to equal on each side. For example, on ethanol, we see 2 carbon atoms on the left side and 2 carbon on the right. We see 5 plus 1 hydrogen on the left, and on the right-hand side, we see 3 times 2 hydrogen, 6 on each side. So the law of conservation of mass and energy comes into role in these equations. But where does the heat come from? While the atoms are rearranging, their electrons are playing a sort of musical chairs. And they tend to go from an orbit of greater energy to an orbit of lesser energy. And the energy that they give up is the energy that we feel and see. Let's take a brief look at wood. Now we know wood can have some moisture in it, which is released when we're burning it, but the combustion of wood also produces similar results to our other fuels, namely the byproduct of carbon dioxide and water vapor plus heat. So the process of burning actually produces carbon and VOCs, much like our other fuels. And there are so many variables with various woods, we're using cellulose in our formula here. However, if we are burning wood in a wood stove, then where does the carbon dioxide and moisture go? It goes right up the flue, right? It goes right up the pipe. So in this case, the moisture is not coming into our work area. The wood is heating the metal wood stove, and it's the heat from the metal that is warming our work area. So we would call that a heat exchange. The wood itself is not heating the shop. The metal from the wood stove is heating the shop. So otherwise wet heat sources can be dry heat sources as well if there is a heat exchange in between. The point is, when we are trying to avoid blushing, heating the air directly with a wet heat source is counterproductive. It's self-defeating. The wet heat source will actually make your situation worse than when you began. Further complicating the problem is aircraft leather, which is often fire-blocked with fire-retardant salts. These salts are hygroscopic, meaning they attract moisture, just compounding our problem. If it's going to be raining for several days, it would be best to wait several days before dyeing the leather. It's better to wait and do it right. And check your weather app. Well, that certainly was a lot of information to cover in a short time. But I think it's good to review that because we want to stay out of trouble when we're working, right? It's better to avoid a problem at the beginning rather than spending all the time and energy trying to correct it. I hope there's something in there that you found beneficial for your business. And thank you for watching, and we'll see you here next time.